Hi, everybody. In the lecture for today, this is part B, or the second lecture for chapter 15. We are going to talk about energy in simple harmonic motion and also the simple pendulum. One thing I'll point out just quickly is there are a lot of oscillating systems. Simple pendulum, which is just a mass at the end of a string, for example, that doesn't have mass. Lots of different oscillating, vibrating systems that if the amplitude is small, looks like simple harmonic motion. And we'll show exactly how that comes about for the simple pendulum. But first of all, let's talk about energy in simple harmonic motion, or SHM, related to the mass connected to the spring that we've already talked about. So again, K is the spring constant, M is the mass, X is the distance or displacement from the equilibrium. And we found that a solution to this motion that describes X as a function of time is given by a cosine function. Take the derivative, you get the velocity negative omega a sine. So we have a sinusoidal type motion, and that really is what describes simple harmonic motion, is that mathematically it can be described by a sine or a cosine. And as we solved the Newton's second law equation, we found that the angular frequency for this system is the square root of K over M. Makes sense. The larger K is, the stiffer the spring, the faster it should move, the bigger the force. The larger the mass, the slower it should move, more inertia, and the frequency should go down. But let's talk about energy. So first of all, we recall that kinetic energy is given by 1/2 mass times velocity squared. And for a spring that's stretched by a distance x, the potential energy is 1/2 kx squared. And again, that came back in Physics 221 when we talked about work and energy. We were able to find the potential energy for a spring. The total mechanical energy, E, is the kinetic plus the potential. Now, if you don't have any friction or any other forces pushing on the spring, you should find that energy is conserved. And by that, I mean the total mechanical energy, 1/2 mv squared plus 1/2 kx squared, kinetic plus potential, is constant. It doesn't change. Now, the constant, of course, is the same throughout the motion, but you'll see, right, when you're at the amplitude, the velocity is 0, and you've got all potential energy at that point. So we can write that 1/2 mv squared plus 1/2 kx squared equals 1/2 k times the amplitude of the motion squared. And this equation allows us really, one of the things it allows us to do is relate the speed, v, and the x displacement at any values. So for example, I could choose a value of x and solve for v, and I would get what the speed is at that value of x. So I don't have to actually use this equation to figure out questions like that. As a simple example, what about at equilibrium when x equals 0? Well, we find that 1/2 mv squared, x is 0, equals 1/2 ka squared. You can solve for v, take the square root of the equations, the 1/2 cancels out. We get plus or minus square root of k over m times the amplitude. Now, square root of k over m is the angular frequency, so it's plus or minus omega a. Now, this is the maximum velocity, right? We can see that again from up here. The sine has a maximum of plus or minus 1. So negative or positive omega a is the maximum value of the speed. And so it occurs at the equilibrium point. Similarly, we can see that when the speed is 0, when the kinetic energy is 0, all of the energy is potential. And as I already said, x is equal to the amplitude for that case. All right, so the maximum acceleration occurs at the amplitude where the spring is stretched the most, but the velocity is 0 there. When it goes back, as the spring is decompressing, it's gaining kinetic energy, losing potential, until its maximum speed and maximum potential energy occurs when x equals 0. Then it goes the other way and just kind of exchanges kinetic and potential energy as it oscillates back and forth. So all oscillating systems do this. We may not have a spring potential energy depending on what it is. So let's look at another example, the simple pendulum. Now, a simple pendulum, what I mean is I've got a mass M, like maybe a rock or something, tied to a light string or a cord of length L. And I'm going to displace it. It's hanging from a support right here. I'm going to displace it, let it go, and it will just swing back and forth. Now, to describe the position of the pendulum, I can use this angle theta, because it's the same all along the length of the pendulum. So what changes is theta, and what we may want to find is theta as a function of time instead of x as a function of time. Now, one thing that theta is related to is the arc length, s, right? The distance along this arc from the equilibrium, where theta is 0. Now, arc length is equal to the length, or the radius, times the angle, if I use radians as my angle measurement. So what causes the oscillation? What is the restoring force? Well, it turns out that it's gravity, right? Gravity kind of acts like the spring in this case, wanting to bring this pendulum back to straight up and down equilibrium. But only a part of the force actually pulls it back, right, in the direction of equilibrium. The other part of the force acts to balance the tension in the string. So I just wrote out my mg. My component here that actually restores it to equilibrium is mg sine theta. So this force acts like the negative kx, right? It wants to reduce, except it's not negative kx, it's negative mg sine theta. But according to Newton's second law, if that's the force, that has to equal mass times acceleration. Now what's changing really as far as a distance goes is s. So I write d squared s dt squared. Plugging in s equals L theta, I have m d squared L theta dt squared. Now, L is a constant, pull it out. Masses will cancel, and I could write my equation for Newton's second law like this, right? Dividing through by the L and bringing things over to one side. D squared of the angle, dt squared, times the second time derivative, plus g over L sine theta equals 0. Now, if you go back and remember what we had for the mass and the spring, we had an equation that looks pretty similar. We've got a second derivative with respect to x. We've got two constants, k over m, kind of similar here. Now, the biggest difference, though, is I don't have a theta. I've got a sine of theta. If I had a theta here, these two equations look exactly the same. As it turns out, when the pendulum has a small amplitude, right, maybe like 10 degrees or less or something like that, it turns out I can approximate the sine of theta. It's close to the angle theta itself. If I make this approximation, take away the sine, the two equations are exactly the same. All I've done really is change the letters, right, the variables. I've changed x into theta, k into g, m into l, and otherwise the equation is exactly the same. So I can see that the solution for theta t should equal an amplitude, or a maximum angle, cosine omega t plus phi. It's exactly like the x of t for the mass in the spring. I'm just talking about the angle now. And the way I compute the angular frequency is I take the square root of g over L, not square root of k over m. So here's my angular frequency for a pendulum, a simple pendulum, that actually oscillates back and forth with a small amplitude. Now, if the amplitude gets big, it's not quite exactly right. So this is a small amplitude approximation. Turns out, any oscillating system, if the amplitude is small enough, you can approximate the motion as this simple harmonic cosine type of motion. If I want to talk about the period, I can recall that the period of the motion, the time for one cycle, is 2 pi over the angular frequency. So for a simple pendulum, it's 2 pi square root of the length of the pendulum over g. So you may use this formula in the homework for this week, for chapter 15. You can also talk about a physical pendulum. Now, a physical pendulum has the mass spread out. So maybe you take a baseball bat and hang it and let it swing. Right? Now the mass is not all at the end in that case. There is a moment of inertia or rotational inertia, and we could analyze that and find an expression for the small angle period or angular frequency 2 in terms of the rotational inertia. And I may talk about that here in the next lecture. But for this lecture, two things again. Energy is conserved for simple harmonic motion. We could apply it to the pendulum. It would be an MGH type potential energy instead of a 1/2 kx squared. The other thing is for small oscillations, the motion looks simple harmonic like it does for the simple pendulum.